Thank you all for being here. We have Esri with us, Peter Becker from Esri. We're going to be talking about how they stage data in S3 for analysis in the cloud. I'm going to get off the stage in a few minutes, but I just want to talk a little bit about something that we have called Earth on AWS and the open data at AWS. My name is Joe Flasher. I'm the Open Geospatial Data Lead at AWS. So one of the questions that I get a lot is, why does AWS care about open data? So put simply, we care about open data because our customers care about open data. So we have a number of our public sector customers that use AWS to make their data open, to make it more available to researchers, entrepreneurs, students, and fellow government agencies for inter-agency sharing. But then on the flip side of that, we have a number of our commercial customers who look to use that data in a scalable manner on the cloud, right? So just like customers rely on us for our infrastructure, I like to think of it as data as infrastructure. So when we think about open data, if you've worked with open data, especially geospatial data, but data of all kinds, anecdotally, it's the case that you spend a lot of your time just preparing the data so you can actually get to ask the questions, right? So that's something, if we see customers doing that over and over and over again, if we can remove that, we call that undifferentiated heavy lifting, and if we can remove that, then we're adding value for the customers. So what do I mean by this in a practical example? So this is an example from Drew Bollinger at Development Seed, and here he's using our Landsat 8 data that comes from USGS and sits on AWS. And I would just like to take a chance to actually thank Peter, because when we made this data available in AWS, he helped us really think about how best to make it available. And so all we did, just to give you sort of a little bit more detail here, is on the left side of this graph is Drew trying to access the data from the traditional mechanisms. And the data is tarballed. So all the bands are put together. This is satellite imagery if you're not familiar with the data source. And on the right-hand side there is when Drew was able to access it on AWS, where we have unarchived the data, and we did some tiling within the data, right? So on the left side there, that's it's a couple minutes per scene for Drew to access it. And on the right-hand side, it's a couple seconds per scene. So this graph corresponds to about 100,000 different requests of the data. And if you do the math, it comes out to about 200 days that Drew did not have to spend waiting to get the data just to do the analysis. Right? And so that's undifferentiated heavy lifting. All we did was unarchive the data. There's no magic here, right? But it's very powerful. So opening the data is just the beginning, though. Users need to understand how to work with the data, and they also need tools to analyze the data at scale. So even if I could give you petabytes of data, and you could somehow store petabytes of data locally, it's probably the case that you don't have enough processing power to work with petabytes of data locally. So when you bring your processing to the cloud next to the data, you have all the processing power that you need, right? So just having the data isn't enough. You also need to have the power to work with it. So this has a really democratizing effect. Anyone can work with the data at scale in the cloud, whereas previously this was the domain of very large companies. So now it's opening it up to everyone. So I'm on the open data team. We oversee the public data sets program. So this is about 6 to 7 petabytes of data that's freely available to the public. There's a bunch of different areas that the data falls into: life sciences, genomics, data that's appropriate for machine learning, and Earth observation data. So I'm the geospatial person, so I focus on the geospatial piece. And we have something called the Earth on AWS initiative, which is a collection of all the sort of large-scale geospatial data sets that you might be interested in, if you're interested in geospatial data. So we've got climate models, satellite imagery, NextRad data from NOAA, GOES-16, Landsat 8, Sentinel-2, Sentinel-1, NAPE data, a whole bunch of different types of geospatial imagery, all staged for analysis in the cloud, so you can work with it. And Peter's going to come up and share a bunch of information with you here in a second. But if anything that Peter says sort of sparks your interest, or if any of the data sets that I just threw out sparked something and you said, oh, I'm already using that data, but I'm not doing it in the cloud, I would like to, we have an open call for proposals to help you sort of prototype what your workflow would look like in the cloud. So please find me afterwards, or just go to the URL. It's a program whereby we can help you with credits to prototype what your workflows would look like in the cloud, because we don't want that initial step to be a barrier. So with that, I'm going to bring up Peter Becker from Esri to talk to you some more. Thank you.
Thank you, Joe. I'm from Esri, so just a very brief slide. Many of you may know Esri. Just as a summary, we're basically a geospatial technology company. We basically manage or provide technology to work with all forms of geospatial data, imagery, vector data. We're used by about 350,000 organizations, use ArcGIS to manage that content in most international governments, in a lot of cities and states. So just a little bit about us. What we have is really one product called ArcGIS. It's really a platform as a comprehensive platform for working with all forms of geospatial information, including imagery. It's a platform for imagery, and I'm going to be talking a little bit about that. What I'd like to do is to break that platform into 3 key components, or actually 4 components. One is what we refer to the system of record, and this is the ability to manage the massive volumes of data. A lot of our customers are large organizations with hundreds of thousands, millions of large images that they have to manage and provide access and analysis to. The next component is what we refer to the system of insight. This is really how do we extract information out of that content and create new information that we can then analyze and create results out of. The third component is a system of engagement, and that's really saying, okay, we can access the imagery, we can access the analysis. How do we combine that into applications that people can interact with and quickly create or get the environments that they really want to work with the imagery and data? And the fourth component is content. We actually provide massive amounts of content in ArcGIS Online, which is sort of a SaaS solution. But we also have a lot of content that is provided by our partners, also content that our customers use within their organizations. So it's a lot of content being used within the platform. We want to talk about imagery, and we talk about imagery, a lot of the questions is, how do I work with imagery? Well, if we rewind 5 years, a lot of people were doing the traditional idea of, we'll download the data into my desktop and work with it in a traditional desktop image processing application. That obviously doesn't scale, and it creates massive amounts of image management problems. The next solution was, okay, let's move all the imagery into a data center, and we will either remotely log into that data center or use web services to access that data. That works. You do performing the analysis near the data, and you only download the results. It works. The question is, how do you scale it up? That's also not a scalable solution. So the third solution, which is really coming into vogue now, is to access the data from the cloud. It's very similar, but you have all the data in the cloud. You only download the results that you need, but you get the efficiency and scalable storage and the compute the cloud provides. There's also massive amounts of imagery already in the cloud. Joe mentioned the Landsat data sets, other organizations. If you went to the plenary this morning, you heard about Digital Globe having 100 petabytes of imagery loaded up into the cloud. So a lot of the imagery is already there. And through that, you can also significantly reduce your costs. You get access to elastic compute and certainly simplicity in how you get these systems set up. So when I talk about imagery, what am I talking about? So we use imagery in a very generic manner to be really a representation of any form that can be broken up into something like a grid. Basically, it's a grid of rows and columns. And what I want to focus on is geospatial imagery. And there are a couple of aspects of geospatial imagery which is different to other imagery, and that is basically it represents something on the Earth. And as a result, we need to come up with a transform of how do we transform the imagery from something from a camera or a sensor to something on the ground which is spatially relevant. So these transforms can be from very simple. The data may have been processed, and it's pretty simple to do that transform, or it can actually be very complicated if you consider you have a satellite flying at hundreds of thousands of miles an hour in space, and how is that related to the ground? So simple to complex. And there are a number of other aspects with this type of imagery. The number of images can be very large, millions of images very often. You have varying bit depths, which is like the measure of dynamic range a bit. You have different type of bands. The data is very often temporal and more becoming temporal. The volumes can be huge, and the number of images can be huge. And you also have important metadata that needs to be handled and stored with that data. So these are sort of some of the challenges related to imagery, and specifically the geospatial imagery. There are also lots of different modes, modes of the data. There's obviously optical imagery, which comes from a lot of the visual sensing satellites. You also have radar. You have things like full motion video, which is video related to the Earth. categorical data, which is really the results of different types of analysis, scientific data. A lot of things like elevation and LiDAR are very often also represented in a gridded form. And then you have a lot of different ways of actually storing the data or structuring the data. So I'm actually going to go a little bit more detail of these, but I'm going to be talking about tile cache, scientific or data cubes, orthomosaic, rectified scenes, and not rectified scenes. And the best way I'm just going to explain through those is actually, I wanted to give some live demos, but I'll just play some videos. It's a bit easier to do. So let's quickly represent the different types of images. The first one is tile cache, and it's really about what you normally see. If you go to Google Earth, Google Maps, or most of the mapping systems, and you pan and zoom around, you see lots of these tiles. If you watch carefully, you'll see the data is broken up into millions and billions of tiles, and as you pan and zoom around, your web browser is just accessing those tiles. So it's a very fixed structure. It's actually very simple to access. It's really structured. It's really structured data. And I'll give you just a quick example. Just go back. So this is what we call world imagery in ArcGIS Online. So this is a data set. It's about 100 terabytes in size. It's accessing anywhere I zoom in, I immediately get access to the imagery. If you look very carefully, when I pan, you'll see that the data is coming up as tiles. So really, this is massive amounts of tiles stored in cloud storage. And as I pan and zoom around, the browser is just pulling those tiles, displaying that imagery, and I get access to the imagery. So relatively simple. Except that you have to scale it. That particular service gets access to, there's 1 billion requests a day that go to that one service. So it gives you an idea of the number of people using that sort of a service. So that's tile cache. The next one is, I'm going to refer to as scientific or data cube data. It's actually very similar in that you structure the data into tiles, but you have a stack of these tiles, and very often you have multiple dimensions to the data. So if we have a quick look at this one, this is actually some data called HICOM. It's data about the oceans. It's basically scientific data. And in this case, I'm just going to basically change between different type of data. In this case, it's water temperature. And it's temporal. In other words, I can go through time and see what the data would be like at any particular point in time. But it also has an additional dimension, which is actually depth. So in the demo, I'm basically turning on the depth component. So you can actually see the data has multiple dimensions. And when I actually pick a point, I see not only how that point has changed through time, but also changed with depth. So you can see we can do a lot more analysis in sort of multi-dimensional analysis. So the data is similar. It's structured into tiles, but it becomes more complicated because we have all these different dimensions that we have to start taking care of. And the applications need to be able to work with this type of data and query it and analyze this type of data. And we can also do more types of analysis. Here's an example where we're actually sending data back to the browser, and then interactively, as I interact with the browser is actually redrawing and displaying this data in a very interactive environment. So you're creating very rich applications by using very rich APIs that the servers actually provide access to. The next one is orthomosaics. There's a lot of this around. These are really images which have been processed into tiles, and multiple images have been stitched together. Again, regular data, but very often they're in different projections. You can't really fit the whole world accurately in one projection, so we have multiple projections, very often with different band combinations. So an example of this one is the nape imagery. It's a data set of actually available in S3. And here we're basically panning and zooming again into a particular area, having fast access. It's 140 terabytes of uncompressed 8-bit 4-band data. So zooming into an area, typically it's used for agricultural applications. Again, I can turn on time and sort of go through and have a look at what did that area look at different points in time. But then I can start doing a little bit more analysis. I can start changing, for example, the band combinations. Here I'm actually going to go to a false color, which is a different band combination. It's what a bee would see, it's different bands. Or I can start computing things like vegetation indices. This gives an indication of how much vegetation is on the ground and is used for a lot of agricultural type analysis. Again, we can go through time and see it. What you have to realize is this data isn't pre-processed. The actual server is actually processing the data as I access it. If I had to actually pre-generate the data, it would be massive amounts of processing that I'd have to do, which I might not actually use. Anyway, mosaics is another type of data. The next one is actually a data set that Joe referred to, which is the orthorectified scenes. This is done very much for Landsat is a typical example, Sentinel is another one, where the images actually have been pre-processed to fit in the ground, but it's actually every scene is an individual scene, so we don't mosaic or stitch the images together, and that gives us much more meta information about each individual scene, but it creates problems because now we have data in lots of different projections and we have irregular shapes between the different images. This can still also be accessed very rapidly, and this is actually a website that Esri makes available called Landsat Explorer, and it gives you access to the Landsat 8 imagery. It's updated every day. It's about 750 terabytes of data. It's multispectral data, so in different band combinations. So it represents the server accessing at any point in time, where there are about 7 million images that are actually available in Amazon S3. And as I'm panning and zooming around, I'm starting to do analysis, looking at different band combinations, getting the servers to analyze and produce, for example, moisture content. What I'm going to do next is actually go through time, and this is a very temporal data set. It goes actually all the way back down to 1974. The Landsat 8 data only goes for a couple of years. But what I can do is to go to any point in time and then actually look at how that has changed, or in this case, I've picked a point and temporally looked through lots of images to identify how did the vegetation change over time. I'm now picking two different points in time, and then what I'm going to do is to get the server to actually do a query to the server and say, what changed between these two particular dates? The server computes this. It returns it, in this case, as an image. Red means there's loss of vegetation. Greens means there's an increase in vegetation. And then if I want to quantify it, I can get the server to actually do the quantification of that, change some parameters, and then if I want actually define an area of interest, which is sort of the area that I'm interested in. So I'm just going to pick the points for this particular area and specify that. And now I can actually quantify and get results. How much vegetation or agriculture changed between those particular dates? So quantifying things. The next one is going even further back, going to imagery which is actually stored, actually captured by the sensors, but is not actually processed. It's left in the sensor coordinate system, so we don't transform it to the ground because it's just too much data to continuously transform it to the ground. So this is an example of imagery which is actually used for emergency response. This is actually imagery from Vexel Imaging. Straight after the recent hurricanes, they actually flew straight after the hurricanes with high-resolution digital cameras and immediately loaded that imagery into Amazon, into the S3 cloud. And ArcGIS server was then able to access that and transform it and perform the processing to transform those pixels into the ground very quickly. And that was incredibly important for example, emergency response organizations as well as insurance industry that need access to this very, very high-resolution imagery. So it's about 24,000 square miles, which was updated basically every day with new parameters. And if I zoom in, you can see the sort of resolution of the imagery and how this can be very, very valuable to a lot of people. I mean, this is just, if I just pause it for a second, you can see the destruction and how this imagery can be used for emergency response organizations and insurance industries to get access to this data. They don't want the data after 3 weeks. They want it the next day, as soon as it's available. And that requires storing the data, getting the data very quickly into the cloud, but then more importantly, providing very fast access to the data without having to wait for all the processing to be done. Even if it's done in parallel, it's massive amounts of processing. So what's happening here is that the actual, as I pan and zoom around, the servers are actually performing that transformation, transforming it from image space into ground space, and providing the visualization as if I'm panning and zooming around on the Earth, but it's actually doing it a lot of computations. So it gives you an indication that sort of data. Another example I want to actually show was referenced this morning by Digital Globe. This is actually a service which is accessing through a service called Imagery plus Analytics. It's a joint project between Esri and Digital Globe, providing users or subscription to 100 petabytes of imagery. You can subscribe anywhere in the world and get access to Digital Globe imagery. This imagery, again, is not processed. It's stored in the, basically what's called a level 1 product, in the image space. And as I pan and zoom around, it's the actual server that is actually transforming the data. It's pan-sharpening the data, which is combining the high-resolution imagery with the low-resolution imagery. It's performing different band combinations, looking at the different data sets, and then doing similar sort of analytics that I was doing with the Landsat imagery. For example, looking at differences, changes between different dates, and then looking at, for example, quantifying what that change is. So the interesting thing here, again, is it's huge amounts of data, which as a user, because it's been stored in the cloud in a very efficient to access format, the servers can quickly access, process, and return that imagery literally instantaneously to the end user application, which may be an application of a human accessing the data, or it may be some analytics that's, for example, trying to look for the location of planes or missile launchers or whatever it is that's actually been looked for. So again, this is non-rectified scenes, data that needs to be processed very rapidly as you access the data. So what was common about those data sets, except for the tile cache? All the data was actually stored on Amazon S3, and it was served using Amazon EC2 instances using the ArcGIS image server technology. So that's really the common thing. It's massive amounts of data. Some of it I would call structured, in that it really is just rows and columns, but some of it I would refer to as semi-structured, because there isn't a direct relationship between anything. There's a lot of querying that has to go on to actually find the data. So let's have a quick look at how is this imagery created? What are the steps that it goes through? So you take imagery from a satellite and you process it to work out where the satellite was, and you get what we refer to the non-rectified scenes. It's really the original images, but we have a relationship to the ground. We then combine that with a terrain model to work out where it fits on the ground, and traditionally that would be orthorectified, and we would get the orthorectified products. Then typically we might stitch the images together to create an orthorectified mosaic, and then once we have the orthorectified mosaic, we then tile it up. Okay? Alternatively, we're talking about scientific data. You might process it directly from the satellite or from the orthorectified data. But each step in that workflow, if you go through it, requires massive amounts of processing, when you're talking about the number of images that we're talking about, as well as additional storage, typically, in each step. Now, people like Western Digital love this concept, because you just vastly increasing the amount of storage required, but it's not exactly efficient. So also there is, I refer to as the first law of image processing, in that as soon as you process the imagery, you're actually losing information content. There is no processing you can do to imagery without it, which actually increases the content. You can only decrease the content. The question now comes, where do I do the analysis? If I do it at the end, I can do analysis, but I've lost a lot of that information content. The more I go towards the raw data, the more information that I get. So what can we do? The tile cache is typically used for visualization. Pan, zoom, millions of people around the world, or billions of people around the world, look at the data and make their own decisions about it. It can now be used also for deep learning. Deep learning is very good, that it works similar to our brain and understands things by its context, and can extract quite a lot of information from that tile cache. If we look at the scientific data, it's used for other things. We're looking at the temporal, going through time, and we use it to try to predict into the future. How have things changed in the past, and what's likely to happen in the future? So it's used for a different type of analysis. The orthorectified mosaics, they can actually be used for a lot of more traditional land classification type projects. We can certainly use machine learning on it, and we can do things like feature extraction, extract the location of things like roads. The orthorectified scenes, these are the individual ones, not mosaic together. We actually have more information, so we can start using more of the temporal component of it, but we can still do different types of classification and machine learning. If we go all the way back to the non-rectified imagery, we can actually do any one of these, but there is more processing required at that point of analysis, because we have to sort of fit it back to the ground. So the further you go back towards the source, the more you can actually do with the imagery. There's a lot you can do with the tiles, but the further you go back towards the source, the more you can do. So Let's talk about the different types of analysis. We split it into two parts. One is dynamic, and that's really saying that, which what I showed, I zoom and pan around, and as I access it, I process only the imagery that I'm looking at, my area of interest, okay? So I only have to process the pixels that I'm looking at. Now, I have to find those pixels out of huge quantities, but once I've found those pixels, I don't have to process billions of pixels. I'm talking about processing millions of pixels in any one instance, but that's computationally relatively easy nowadays. So we get results directly. The other one I would refer to as persisted, where we use things like global functions. If I want to accurately compute how much vegetation changed between two different dates, I actually have to go and read through all that imagery, okay? So the system has to basically chunk its way through all the data. And that means we actually do have to process very large extents, very often at very high resolutions. And all the pixels that are required for that analysis are going to have to be read, and I'm going to have to create an intermediate product to somehow store that information. So we need to store those results, and that actually starts bringing up challenges when we start talking about these global functions as opposed to the dynamic, global as opposed to the local functions. And there's a lot of analysis when you do things like working with digital terrain models. How does the water run through across the ground and things like that, where you have to analyze, you have to know not just the pixels that I'm looking at, but the water could have come from the other end of the country, so I have to do a lot of this global analysis. So to do all this, we need to do a couple of things. Well, we have to manage this data. We need to store the pixels, and we have to somehow index them. And depending what we have between tile cache and non-rectified, the complexity of that indexing becomes more and more complex as we go through that list. But we also have to then be able to apply things like the projection, rectify, auto-rectify the imagery. We have to handle things like masks of cloud and metadata about it. And we need to apply a lot of different image processing functions, like how to handle the atmosphere, how to resolve or pan sharpen or fuse different images together. So there's a lot of image processing that has to go along. And the way we manage that is through a concept called a mosaic data set. It's actually a data model which is used to reference all the imagery. It's really a relational database which has attributes for every single data set in there. It has attributes about that data set which I might use for searching it. Find me all the images where cloud cover is less than a particular value. It stores the geometry. Where in the earth is that image off? It has references to the data. We certainly don't want to try and load those pixels into a database. It'll kill any database. And it also needs to store within it the georeference or the processes of how to transform those pixels from what are pixels into what I actually want to see. Okay? And these databases can be large, very often containing millions of records. And we can store those either in what we refer to as a file geodatabase, which is a very simple database that you store on a local machine, or an enterprise database. And very often we use things like Postgres, and RDS is perfect when we move to the cloud, is to store that relational database in something like RDS. Then we have the raster functions. This is, okay, I've got an image. Now, how do I actually process that imagery? And what we use, ArcGIS has these concept of raster function, which is a way of putting together or stringing together all these different functions together in multiple ways, because there are an infinite number of ways you may want to process this imagery. But to do this to efficiently, what you need to do is to concatenate these functions together and reduce the amount of input-output, because that otherwise will just kill the system. So ArcGIS has about hundreds of these different functions that you can put together in these models to define how to process the imagery. What's also available is the Python raster function. And that is actually very important. That actually allows us to integrate with Python, which is becoming a standardized way of doing all types of computation with array data, especially using NumPy and SciPy. There are fantastic libraries becoming available, or that are available, that can be then very easily integrated as part of this chain of how the imagery is processed together. So these function chains really define how pixels are transformed from the source to the output for any area of interest. Now we have what we call dynamic mosaicing. And this is the aspect of, okay, we got the database of where the images are. We have functions which define how we want to transform the data, and how do we actually put this together? So the system has to, when I zoom into a particular area, so I've zoomed into one particular area, the system has to determine, okay, which images are appropriate. So I have to query this database, find out all the intersecting images, then I have to order them based on a rule. Well, which image do you want on top? Is it the last image, a date from a particular range? There are all sorts of rules that define which image should go on top, and there may be multiple images. Now, for all those contributing images, I have to go and read that images from the source, wherever it is, in S3, hopefully, extract it, and I have to apply multiple different functions, because every image has to be processed in a different way. They all have different spatial relationships and stuff like that. So I've got to do all those different processes. Then the result I have to mosaic together, because I got lots of images, I've got to stitch them back together, and there are lots of different rules about how we stitch them together. Do we blend them? There are different ways of bringing the images together. Then there may be additional functions that I want to process on top of that. And then I've got this imagery in memory. Now what I need to do is to somehow get it to the client application. It's pretty big, so I've now got to compress it and then transmit it across. So this is all the stuff. When I was going through the demos and panning and zooming around, it can be done in a fraction of a second, but there's a lot of stuff going on in the background. This is not just pull down a tile and display it on your web browser. This is make a request, and the system has to try and do all this work and get that result back to you, typically within about a second. There's a lot of processing going on. So the way that's done is using our ArcGIS image server. And the image server has basically, in concept, it's very simple. You have your mosaic data set at the bottom, which stores all this information about all your images. And you have your data source, and you put your server in front of it. And now the client applications make requests to that server, and the server then performs that processing. And those requests come in different ways. They could be REST requests. They could use OGC, WMS, WCS, KML. There are lots of standards that need to be supported about how this imagery is processed. And the REST type requests are very advanced in that it's not just saying get image or give image. It's no, this is the analysis that I want to do. This is the processing I want to do. That has to be transmitted to the server. The server then has to do the processing that I've requested and then return that imagery together. So it's quite a detailed APIs that are required to handle all the different types of data, not only the pixel data, but the meta information, the spatial references, and stuff like that. So that's how we do the dynamic image services. But what if we want to scale this to use the global functions? Well, it's actually exactly the same product. It's just a new capability of the system, which we call Raster Analytics. It allows us to actually scale those servers out. So in an elastic environment, it's not just one server, it's 10 servers, 100 servers. You can actually scale this up and scale this back down again. So these servers are doing very similar type of analysis, but instead of just doing on one area of interest, it breaks the problem up into potentially thousands of areas of interests, does those all in parallel, and then has to stitch this all back together. Now this becomes interesting. How do I actually start writing all this imagery back to a data source, or all the results back to a data source? And that's where we really need to have these distributed raster data stores, which are ability for the service to write multiple services, multiple processes to write simultaneously to the same data source, be that a raster data source or a vector data source. And then we want to try and integrate that with other systems as well. ArcGIS has a lot of capabilities, but there are a lot of things that we don't handle directly, we call out to. Hey, you want to call out to TensorFlow or something like that, or CNTK, or other analysis, or other applications that may be running in Lambda or something like that. And ArcGIS allows us to do that. So these tiles, or internally that are handled, can actually call out to other systems so that they can actually perform the processing and return those results back into the ArcGIS system, either through the same pipeline or feed it directly to one of the data stores. So that's really how the system works and puts the data together. And to give an example of this is, one is creating a solar suitability model. This is really a model to try and identify, if I had a solar power plant, where in the United States would I put it? And that requires taking a number of different data sources, rainfall, mean temperature, elevation, all these different data sets, and creating a model which tries to work out the best location based on these different things. And that's basically a model that can run, and within the desktop environment, that certainly runs. We can run that. It takes about 6 hours to run that for the whole of the United States. If, on the other hand, we move that to Raster Analytics and set that up on AWS with 8 C3 machines, that computation went down to 9 minutes. And that's the difference between running something and getting the results tomorrow and having a coffee break and getting the results. So you can see how the parallelizing these processes really substantially reduce the time. Another example is running basically land cover. This is basically trying to identify, what is each part of the ground at very, very high resolution. In this case, using NAPE imagery and processing it through basically image processing chains, which have to change the band combinations and do things like segmentation and classification on the data. So there's quite a lot of processing going on. Again, this has to be parallelized, and we basically did a quick test on it, took a whole state of 1 meter land cover imagery. It's about 100 billion pixels, 400 gigabytes of data needs to be read, but it can be processed in just over an hour. So, sort of architectural diagrams, we have what we call ArcGIS portal, and that is really the core component of the system that manages everything. It also provides the content management, content control, who can access what. And then we have these image servers which are either performing the dynamic image services or the raster analytics, and those are then connected with things like load balancers, connect with RDS where the mosaic data sets are typically stored, and then store the data or read the data from S3, which is typically where we actually read the data from or write the data output. So let's go into a little bit more detail on these imagery. We got lots of imagery, and Joe mentioned the fact that, well, if you do it wrong, it can be horribly slow. So there are a couple of things we need to look into. One is we need to work out how we're going to store the data. And Amazon provided a number of different storage options. The first question is which one to use. So we have EFS, S3, Glacier, EBS, and ephemeral storage. Each one of those has advantages and disadvantages that I'm trying to outline here in terms of cost, capacity, latency of accessing the data, throughput, reliability, what happens when it goes down, and can the data be shared between multiple machines? So we need shared access. Obviously, I got 100 petabytes of data, and I want lots of machines accessing it. So that reduces it. It certainly has to be very high reliability. I want high throughput. I want low latency. Not any one of those is actually going to answer all those questions. But you can really see that there is only one sensible solution to that, and that's to store the data on S3. That is the only thing that can really handle the petabytes of data, but provide the throughput and latency that I actually need. Although the latency of S3 is relatively high, the throughput is pretty good, but it's not excellent. But we also have the ephemeral data, and that's actually included in some of those machines, and those give you very fast access to data, but only if you can get it on there, and if the machine goes down, that's all gone. So the trick is really to take in consideration the advantages and disadvantages of the different data stores, and the trick is to use both S3 and the ephemeral data. So what affects performance? Well, one is certainly the volume of data read. If you're reading a whole lot of data and it's just full of clouds or no data values there, you're just wasting your time. So what you need to speed it up is, one, to ensure you only read what is required. And that's really what the mosaic data set's doing. It's providing that index to tell you which pixels you need and which pixels you don't need. And that's why we use things like footprints to define the spatial relationship, because if you have a lot of overlapping images and they have areas where there is no data, I do not want to waste my time even trying to get at the data, because I'm just going to get a bunch of no data. So the spatial footprints actually solve that problem. I also need to reduce the data access by tiling, and I'll come back to it. I also have to create the processes which are very efficient. I have to reduce the I/O, and the way to do that is to concatenate these functions. So I reduce the amount of input and output between the different processes, and the raster functions do that. I need to reduce the latency, and there are ways of doing that. One is to use storage, which is very fast or very low latency. The other trick to do is to stop reading things that I've read before. So there's a lot of very often duplicate reads going on. If I get rid of those duplicate reads, I speed things up. The next thing is to reduce the bandwidth. So I can do that by compressing the data. Problems. If I start compressing the data too much and it becomes lossy, a lot of people, the scientific community especially, say, you're not doing that. So very often we have to use lossless compression. And we have to be careful with the compression, because when I compress data and decompress data, that doesn't come for free. There is CPU cycles required to do that. And there are certain formats which are pretty CPU intensive. And what you'll find is that most of your CPU has gone to decompress and compress the data just to get a little bit more storage, which doesn't make sense. And the last point is how to structure the data. It needs to be very efficient. So let's have a look at some imagery and look a little bit more detail in the different formats, and what we do to the formats to speed that up. One is to tile the data up. So at the bottom, I actually have a diagram which tries to represent a typical TIFF file, a raw TIFF file. It's actually what you would get from most data providers still deliver the data like this. It's just a header with the metadata, and then rows of images, rows of pixels, one after the other, and then maybe some metadata at the end. Now to zoom and pan, if I zoom into any particular area, I got a lot of pixels. I got to read a lot of unnecessary pixels to actually get access to it. The next one is, which is much better, is to actually use something like GeoTIFF, or tiled GeoTIFF. Basically, it's very similar, but what it does is it tiles the data up into tiles, and those tiles typically can be compressed with various methods. It also creates a pyramid, which is a reduced resolution data set, which means that if I zoom out, I can quickly get an overview of the image as opposed to having to read all those pixels. So GeoTIFF is certainly, it's pretty good. It's actually a very good way of structuring the data. There is another improvement which has actually been made recently called Cloud Optimized GeoTIFF. A number of projects have gone, especially in something GDAL, I'll come back to this, to further optimize how GeoTIFF is read. And they say, what we're going to do is we're going to move that index to the top and the metadata to the top. And now one request can actually read, one request will typically get the metadata, the index, and maybe the overview of the data. And therefore, I can reduce the number of requests going through. It's a pretty good idea. Another way to do it is another format called MRF. It's actually a format that came out of NASA, which actually says, nah, let's not stick everything in one file. Let's split it into 3 files. We'll have one file with the metadata. The metadata is very, 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 very small. We're talking about a few 100 bytes of data. We will put another file for the index, which is also very small. It's just basically an array pointing to where the data is. And then we're going to leave all the other imagery somewhere else. And the breaking it up into those 3 files is actually very interesting because it actually exploits aspects in the cloud of caching. When you store something as a small file, that's actually going to get cached by the system. If I access it, it's going to be cached all the way through it because I can basically make a GET request to it. If I try and get it, I'm not going to do a GET request to the big data. I'm going to have to do a range request. And as a result, that's not going to get cached anywhere. So splitting it up actually optimizes it. What we can also do then is be sneaky and say, well, let's actually just copy that metadata in the index, which is actually very small, and store that locally. So I don't have to go back to S3 to get it. And that's what we refer to as a Raster proxy. It's a way of storing the metadata locally, which is very small, so that I don't have to go back to S3 to get it. What I can also do is to create another index, which is the data that I can store the pixels that I've already read from the cloud, from S3, and store those locally in my ephemeral disk. And that's the concept of a Raster proxy. So what I'm showing you is the different ways of accessing the images and the advantages and disadvantages to it. The next one I need to handle is how those formats that I mentioned before, they're good for reading data. You don't want to have one huge MRF or GeoTIFF or COG file covering the whole country at 1 meter resolution and then trying to write to it. It's not going to work. So we have to basically have another format. And this is a format called CRF, or Cloud Raster Format, which is a way of taking the same concept and breaking it up so that those data sets can, in theory, be shrouded. It becomes a data structure where each directory has a different level of the pyramids, and the actual pixels, with these tiles, we actually put into bundles. So we put lots of tiles together in these bundles, but we also have lots of bundles. We have to manage those. But the advantage now is that when multiple processes write simultaneously, each one of them can write to a separate bundle, and you can have parallel write. So that resolves the problem of parallel write. So these are the sort of different formats and why the advantages and disadvantages. So what we wanted to do is to actually test, how does this actually work? It's all great in theory, but let's actually do some tests. Now, how do we actually read imagery? Well, Esri and nearly every spatial company. How many of you use GDAL? Okay, I was expecting at least half of you. So most people use GDAL to read imagery. It's an open source library, very well used. A lot of companies, including Esri, contribute to its development. And it's really the main way that geospatial imagery data is accessed. There are some dedicated APIs, and there are some advantages of using dedicated APIs as well, but most people actually use GDAL. So I'm going to be focusing on using GDAL to read the data. So let's actually have a look at these formats and the advantages and disadvantages. There are things like formats like HDF, NetCDF, GRIB. These are data sets used in the scientific communities. They're very good data sets. When they were designed, the concept of a cloud was not around. Well, cloud was around, but it was a sort of a white fluffy thing in the sky. It wasn't anything what we consider cloud here in this conference. So they were not really optimized. They were actually very slow and complex to read and aren't optimized for the cloud environments. You have other formats which have come up also at the end of the last century, which were things like JPEG 2000, Mr. SID, and ECW, which use a different type of compression, what's called wavelet compression. It actually gives a little bit better compression, but it's pretty CPU intensive in most cases, or very proprietary and only readable in certain systems. And again, it's not really designed for working on the cloud. TIFF is flexible, but it's also not cloud optimum. And then we have GeoTIFF, which is flexible and performant. We have COG, cloud optimized GeoTIFF, which has a little bit of advantages. It does have a disadvantage, mind you. I have to reorganize this data. When I write the data, remember those indices have got to somehow move back to the end, but I don't actually know them until I've finished writing the file. So I have to go and reorder the data. That slows down writing the files. Also, there's the MRF. It has a number of advantages. It's actually extremely simple, which is actually good. It has the split index. It has what we call lurk compression. I'll come back to lurk in a minute, as well as something called Zen JPEG, which is a way of handling transparency in JPEG. One potential issue, some people might say, is it's not as widely used. It's all open, but it's a relatively new format, so there are not that many organizations using it, although GDAL reads it perfectly. There are other ways of doing it. People say, just split everything into billions of tiles. That's a nice concept, but it doesn't really work. It becomes extremely difficult to manage, billions of tiles, and there's actually a high cost because you do have to start taking into consideration the put and the guest costs that Amazon will charge. Then there are things like compact cache, which are a little similar, an older concept of CRF, which are really have the benefits when we start, compact cache and CRF have benefits when we're talking about these very, very large single files. Coming back to compression, you have different types of compression. I'm just highlighting the main ones here. JPEG is very fast. It handles typically only 8-bit, although GDAL does handle 12-bit. You can have JPEG 2000. You get higher compression. It's not that much higher. You can argue about what the value is. I reckon it's about 30% typically for the same type of compression, but it's typically much slower and has high CPU usage. JPEG and JPEG 2000 are typically lossy. In other words, you change the values a little bit to get better compression. The lossless is deflate or LZW. They're very similar, flexible and performant. JPEG 2000, you have a lossless version of it, has the same issues with as I've mentioned previously. And then you have lurk. Lurk is actually a compression method that Esri came up with a number of years ago. We actually patented and then actually released that patent to the geospatial community. It's actually very fast, it's very simple. It actually provides higher compression than things like deflate. And it also has some other advantages in integrated things like no data, and you can actually read it through things like JavaScript. So it's a very simple way, and it's very, very efficient to actually read. The problem with it is it's only supported in MRF at the moment. So we did a test. We took 50 files. These are 4-band, 16-bit, pretty large files. It's equivalent to about a 90 megapixel camera. And we actually converted that data into different bands, different bit depths, and using different formats, cloud-optimized TIFF, GeoTIFF, MRF, and then also with different compressions that were available, deflate, lurk, and JPEG. We did similar tests on other data as well, just to confirm that there was no outliers and everything works similarly. So this is actually what comes out of it. From a file size perspective, when you actually take GeoTIFF and you have deflate, so what I'm showing you here is that from a lossless perspective, there's no difference between using cloud-optimized GeoTIFF and GeoTIFF with deflate. There's not going to be any difference. Similar with MRF, there's not going to be any difference. If we go to the lurk compression, we actually do get benefits. It can be a few percent. On the 1-bit, 8-bit imagery, it's about 22%. So when you talk about large volumes of data, that becomes quite significant. Again, this is just totally lossless, and it's not using one of the advantages of lurk, which is this controlled lossy option. When we go to actually the JPEG versions of it, this is the lossy compression. The compressions, it doesn't really make a difference whether you're using COG, GeoTIFF, or MRF JPEG. Size-wise, it's actually the same. The interesting thing is the file sizes are certainly significantly less. They're about for the 1-bit, 8-bit imagery, so that's sort of just 1-band imagery, it's about 4.5 times more compressed than the lossless. And for the RGB imagery, it's about 10 times. So it's compressing a lot, but there is some loss in the data values. So for certain applications, it's not applicable. The interesting thing is the conversion time, mind you. The cloud-optimized GeoTIFF, because of this rearranging of the data, takes about 25% longer to do. And the lurk, because of its very efficient compression, is actually 25% faster. So actually, the MRF with lower compression actually is smaller and faster than the other methods. Now we want to read the data, and the way we read the data was to actually, not using ArcGIS, we're actually just using GDAL, just using the latest version that just came out, 2.23. And what we do is we take the images, and then for each imagery, we just read different areas. Some of those, you see those areas are overlapping, and we just try to see what happens when we reread similar areas. And each of those are different sizes. So we run that on a test script that runs 8 of these processes in parallel. We record the times, and then we run this thing multiple times, again and again and again, and record really the lowest time. Because within S3, it's not always the same response. It's sometimes a little bit faster, sometimes a little bit slower, so we just run it multiple times and just take always it should be the fastest time, not the lowest time, which is the fastest, yeah. So what comes out of this? So again, as a comparison, I'm just going to use cog deflate as the comparison. And if you look at the results, you see that cog, because of the way it's structuring the data, is actually faster than the deflate. But MRF is actually, again, quite considerably faster. Okay, so we get benefits, and this benefit is basically because of the way the data is structured. Now, in this case, I'm not using raster proxies. In these tests, we were just reading the data directly, yeah? And you can see that the times, typically, for the lossless data, we get access times between 20% and 45% faster. For the lossy compression, it's about 45% faster. So this actually is quite considerable in the time. And this is for reading the data. And if I go back to the slide, you saw that I repeat some of those areas. And if I actually directly access the data and compare the first read to the second read, because of the way the data has been read, I read all the data and then I read it again, that difference is about 1% between the two. If I use the raster proxies, mind you, then I suddenly start seeing something else. I get an additional 30%. So the raster proxies just mean that I just collect all that metadata and store it. Just how many bands and rows of the imagery there is. I store that locally. It's extremely small. And because I have that, when I access the pixels, I don't have to go and ask what it is. And that gives me a 30% improvement, just like that. Then, because the raster proxies cache the data as well, the second time I go back to that area, which happens very often, think of somebody panning, zooming around, a lot of those pixels are the same pixels, I actually get about 65 to 75% further improvement in the subsequent requests. So when you start actually adding up each of these percentages, you actually get quite considerable improvements in performance. So just a little bit more information about how this is done. There are some tools that Esri provide. It's actually in GitHub. It's open source called Optimized Rasters. It's really just a wrapper around GDAL Translate and Boto and things like that to simplify the way that if you have large collections of data, how do you take that data, convert it, and move it up into the cloud? And that conversion can be done at your desktop, or you can actually move it up and use things like, it actually integrates with things like Lambda to use Lambda to do the parallel conversion of the data. Very, very useful tool. It's out there. I recommend if you're interested in moving the data to S3 or cloud environments, look at Optimized Rasters. It's a great way of moving the data up there and doing that data transformation. It can be accessed as a command line and script. You don't need ArcGIS installed, although if you have ArcGIS installed, you get much better tools that show you how to set all the parameters very easily. So something worth looking at. So in conclusion, there is significant value in moving the data to the cloud, especially for imagery. For a lot of our organizations, it's the first thing the first type of data they start moving to the cloud is imagery because of the value that can be gained. S3 is certainly the way to go, but you have to be careful what you're doing. You have to think of how the data is structured when you do it. Don't just move it over there and expect everything's just going to work. You need to ensure the data is managed appropriately. Things like the mosaic data sets are a fantastic way of doing that. ArcGIS provides that platform then for integrating all forms of spatial data, so including imagery. So certainly look to the platform, the ArcGIS platform. And performance comes from not one aspect, but really optimizing lots of aspects of access and processing of the data. Use compression carefully. It can slow things down. If used correctly, it can speed things up. Look at the format of the data is important. Look at MRF as a format. It has a number of advantages in speeding things up. And also look at these raster proxies as another way of speeding up the access. And within ArcGIS, you get all that as part of the platform. So with that, was the end of that. Thank you very much, and we'll be open to questions.
Thank you, Peter. Based on the number of pictures that people are taking, especially of your architectural diagram, I think this will be a wonderful resource that people will look for in the future. And just all of you, just remember that slides and videos both are online, right? So you'll have a higher fidelity than probably what you managed to take with your photos. So we have a few minutes, I think, for questions, if there are any from the audience. Yeah, we have 5 minutes.
No.
Yeah.
Yep. Yeah, okay. So the question was, if I have MRF and I want to access it with JavaScript, as I mentioned, you can actually use JavaScript to access the MRF files. Is that doing directly from the browser, or is it using the Raster proxies? So the MRF format, as I said, it's a very, very simple format. It splits it into 3 files. So you just basically get a GET request to get the header. You do a GET request to get the binary index. And now from that, you can do a range request to identify which tiles you want to read. And if it's look compressed, there is JavaScript which will actually decompress that look very quickly, and you get an array in JavaScript. So that you can run really, really easily. In that case, there is no Raster proxy unless, yeah, because in theory, well, you can't because you're doing a range request to S3, and a range request will not be cached by the system. Okay? The index will be cached, and the metadata will be cached, but because the tiles have to be done with a range request, you have to actually, that will not be cached. There are ways of getting around that, mind you, if you actually put a proxy in front of S3, which you then request, which then you actually give it as a HTTP GET request, and it then converts it to a range request, then caches it and brings it forward. We don't actually provide that, but that is one way that you could actually speed that up if you wanted to actually get the caching. The problem with, as I said, the range requests is it will not be cached by the systems. Okay?
Yeah.
What version of GDAL started using MRF? It was from 2.0, definitely. I don't know whether it went to 1.9, but it's certainly in 2.0. On Global Mapper, I don't know.
This is for open data. There's retention policies regarding Lotus data. Is that continual? Because there's like a 30-day retention policy for a lot of Lotus data sets. Is that the plan going forward?
Are you speaking specifically about the Modus data that's on AWS? I do not believe we have a 30-day retention policy. I think we just hold on to everything. On our own landing page? I forgot. Yeah. So, I mean, the general answer is that it varies by data set. Really, the reason why we go after the data sets and when the retention policies get set is based on customer uses. So, find me after, if you have a reason to have it longer, just reach out to us or talk to me afterwards, and we can sort of review that. But yeah, it's all based on customer feedback.
Okay, well, I will be here for a bit longer if anybody has any other questions. Otherwise, go party. Thank you.
Thank you all.